podcast is brought to you by LMU Munich.
Yes, good. Yeah, so welcome. So I'm Ralf Blumenhagen. So I'm a member here of the Max Planck Institute for Physics in Munich. And I was asked to tell you something about open strings. And so I decided to do on D-branes. And I decided to stretch that a bit. So that my lecture is about open strings. Actually, it's called D-branes and Orientifolds. So, and in fact, you will see we will start very basic with introducing open strings, quantizing them, and this will bring us to the concept of D-branes as new objects present in string theory. And if we have arrived at the concept of D-branes, it's very easy to generalize this concept to what is called Orientifolds, or Orientifold planes. And this I will also discuss. And my final aim is, hopefully I will get to that, at the very end, to tell you or to derive you what the type 1 superstring is. So the aim is to derive that the type 1 superstring in 10 dimension has gauge group S or 32. Okay, so that's a long way to go. And there are also lecture notes for that. And this essentially is the 6th chapter of this book here. So this is the lecture notes I gave, I think 2 years ago and 3 years ago. It was a course on conformal field theory. But in the very end, I was also discussing, from the CFT point of view, D-branes and Orientifold planes. And the lecture notes you will get is precisely the 6th chapter of that book, which covers most of what I will tell you here and even covers a bit more than what I will tell you here. Okay? Excuse me? You just want to see the book again? Okay, so I'll write it down now. So it's by myself and my former student, Eric Plauchin. Who did a lot in pushing my handwritten notes into this book here. And it's called Introduction to Conformal Field Theory. And the subtitle, which I won't write down here, is With Applications to String Theory. So it has particularly, this is just a formal theory, but in particular, we will discuss those issues of CFT which are related to string theory. And had appeared in Springer Verlag. So it's lecture notes in physics, lecture notes physics, 779 Springer. So you're not meant to buy it. I just want to, because you get the lecture notes anyway for free. It's also available. I hope it's not. I hope it's a true copy and not. Also on the internet, you actually have to pay for it, I think. So if you get it for free, you should be suspicious. Okay, good. So, then let me start maybe. So we'll start very basic. So we go to chapter 1. So this is about a free boson. With boundaries. So what this means is, so if you, I guess what you have seen in the introduction by Neil is that he has quantized string theory for you, and probably he has just quantized closed string theory. I'm not quite sure about that. But so what you do is you start with your string theory in flat space time, and from the conformal field theory point of view, so from the two-dimensional action point of view, so you write down an action on the string world sheet. So you have an integral over the string world sheet, two coordinates, then an appropriate gauge. So after a little bit of massage, and I guess this is what he has shown to you, is that you can write this as a theory of just a free boson in 2 dimensions without a mass, so massless one. So I'm looking here in Euclidean signature. Okay, so I hope you have seen that. Yeah, this just for single fields. So usually you write down here some index mu and take trace of that. Okay. So just to repeat, so now if you vary this action with respect to this free boson field, and you use, for instance, that nabla on nabla x, so you have to generalize partial integration for this case. So we vary it, so we have a variation of x mu by delta x, and then you can write this as the D'Alembertian on x times delta x plus nabla x square. So if you insert that, so you vary this action and you use this formula here. Maybe I should write a little bit smaller. So then you get delta S is equal to, so I mean, I'm not caring about normalizations here. So you have d squared sigma minus box x delta x plus nabla delta x, yeah, which is the vanishing of that, so we require that this vanishes. And the first term, it's obvious that this just tells you the wave equation for x, so it follows that delta x has to vanish. Yeah. So this is just the Klein-Gordon equation for a massless boson in 2 dimensions. And now if you apply Stokes theorem, so here's a complete divergence here. If you apply Stokes theorem to this term here, so you write Stokes, and you get delta S, the second piece, proportional to integral delta x times the normal vector. Okay. Delta x. And you integrate over the boundary. So if this is your worldsheet sigma, here you integrate, because you have applied Stokes theorem, over the boundary of the worldsheet sigma. Okay, so this is the vector, some strange normal to d sigma. Okay, so usually what you say is, okay, so if you have a closed string, apparently there is no boundary. There's no boundary, the second term vanishes, and you just get these equations of motion for a closed string. But if there is a boundary, this is the case we are considering now, because we wanted to discuss open strings. In this case, there is a boundary, so we also have to set the second term to 0. Yeah? And if you do that, there are 2 possibilities, apparently. So I have one picture actually here. So what is the situation? So now here you have your open string. So here's sigma coordinate, and this direction is tau. And the usual normalization is that, so if a closed string has length 2 pi, an open string is half of that, has length pi. This is the convention we are using. And then this would be the boundary. Now this whole thing is sigma. This is the boundary, and it has 2 components. And this is the normal vector. Yeah? Okay, so now, if we now require delta SB equals 0, so we get 2 different ways of getting this term to 0. So either this thing is 0, so the variation on the boundary is 0. So the endpoint of the open string is not allowed to move, or this term is 0. Yeah? So this allows for 2 different boundary conditions. So this is the normal vector. So this means that the variation of the field along the normal vector is vanishing. So this is the partial differentiation of x in the sigma direction. Yeah? So this means, so the first term vanishing means that, in other words, the sigma of x at the boundary, which is a sigma 0 and pi, is vanishing. That's one possibility. And the other possibility is that there's no variation on the boundary at all, so that the endpoint stays fixed forever, so that this is 0, which also means that the partial derivative with respect to worldsheet time is vanishing. So we have these two possibilities. They also have a name. So these are called Neumann boundary conditions. Neumann boundary condition. It's very similar to what you do in electrostatics. Also, the names are the same. And these are Dirichlet boundary conditions. Boundary condition. So we have these two possibilities. And the fun thing is that historically, for I don't know how many years, 10 years at least, people have mainly considered only the first boundary condition. Yeah? And it was only with Joe Polchinski actually, for the first time, and it was really the mid-90s when it appeared that also the second boundary conditions are really important. And there's a whole new structure of string theory hidden behind the second boundary condition here. That looks so simple, and you cannot imagine why people have neglected that, but indeed they had. And the whole thing about D-branes is about the second boundary condition. I will explain what this means. Okay. It's very slow. I can't have two of them. Okay, so now let us exploit what these boundary conditions mean for our string. So for doing that, it's convenient to use not sigma and tau, but just to remind you, and that I think this has been done by Neil, so to wrap everything to the complex plane by using the map that defines z is equal to e to the tau plus I sigma. Now, so for the closed string, sigma was running from 0 to 2 pi I, so this really makes sense. This covers the whole complex plane. And the radius of the complex coordinate is related to the time on the worldsheet. So, and this now maps, so the closed string is mapped by this map to the whole complex plane, but the open string is not, because it only has a length pi, so it's only mapped to half of the complex plane, and more precisely to the upper half plane. So this is the complex plane. So I can do this here. So lines of constant tau are mapped to semicircles here, like that. And past infinity is this point, and future infinity is infinity. So this is the map. Going from here to there. So this point here corresponds to tau equal to minus infinity. Okay, and now we would like to see what these boundary conditions mean for the quantization of the string, or for the modes of the string. So the string has to satisfy, obviously the free boson has to satisfy the Laplace equation in 2 dimensions. The solutions, this is a wave equation, so these are right moving and left moving waves. Hope this has been discussed. And now we have a boundary condition, so we can expect that these two modes, one moving left, one moving right, there's a boundary, so they are reflected. So there's a relation between left moving modes and right moving modes. This is what you physically expect. And indeed, this comes out after we do the following simple computation. So in this complex coordinates, there's a mode expansion for this field x. So remember, so I'm just discussing one field, but you can always, introduce an index here, and then you get all 26 directions of the bosonic string, for instance. And what you can then do is you can have certain coordinates which satisfy Neumann boundary conditions on both sides, and you can have other coordinates which satisfy Dirichlet boundary conditions on both sides, or you can even have open strings which satisfy Neumann on one side and Dirichlet on the other side. So all possibilities can be realized, and we are just discussing now is just a single coordinate and what these boundary conditions mean. So we expand this, so as I said, into left and right moving modes. So left moving mode, which only depends on z, and what's called the right moving mode only depends on z bar. So these are, in the other coordinates, these are really left and right traveling waves. And for XL, let's see. So you can make a Fourier expansion in the tau and sigma variables, which become a Laurent expansion in the complex coordinate z. So there's a center of mass position here. Then there's pi 0, half. Then there's what is called the center of mass momentum of the string. And then there are the various oscillator modes of the string. I mean, this has been discussed, I hope. Is Neil here? This has been, yeah. You have discussed that, right? Or hadn't? Yeah, okay, but I mean, because somebody looking like, I'm talking something, out of this world. Okay, so you have seen this. Good. So then I can continue with that. So you have, then you have the oscillator modes, alpha n over n, z minus n. And the same or similar thing for the right movers, which just depend on the complex conjugate coordinate. C plus I. Okay. So, well, I could have gone, okay. Yeah, there's one step in between. So now if I use these coordinates, I could have started right away because you introduced it in the other way. Sorry for that. So in these coordinates, so you have left moving. Excuse me? Yes. These two are the same, and these two center of mass momentum. So like this is also the same. You get a difference. There's subtleties here. You get a difference if you are. I tell you just that if you consider this theory on the torus, then you can distinguish. Then you have the winding modes as well. If you have the winding modes, then the center of mass left moving and right moving center of mass momentum can be different. But I haven't introduced winding here, so this is why they're the same. Yeah. Yeah. Okay. It was not perfect, but let me write it now in the other coordinates, because then here I just have tau. This is now the whole expansion, the sum of these two. Okay, so now what you do is you just require these boundary conditions. Yeah. So there are these three cases I was discussing, or I was mentioning, that you have Neumann boundary conditions on both sides. So you have Neumann on both sides. At both places. And now it's a straightforward exercise. If you introduce this, I can also do it for you if you want. So you have dx d sigma. This gives you, so here's no sigma dependence at all. So this gives you n, then you have alpha n minus n and then minus alpha n bar to the minus n, there's no n here, and tau minus I sigma here. Yeah. So, and this I require at both positions, sigma equals 0 and pi. So if I do it at sigma equals 0, so this term isn't there, it has the same exponential function here depending on tau. So this just tells you that, and this has to be set aside for all n, that alpha n has to be equal to alpha n bar. So that the left moving excitation is the same as the right moving one, which is just this reflection at the boundary. So this implies that alpha n is equal to alpha n bar. And from the second condition, at pi, you find that condition on these modes n, that n has to be integer. And so this is comes from the second boundary condition. Yeah. And you can do the same. Maybe I squeeze this in here somewhere. For the case that you have Dirichlet boundary condition on both sides, it's not very much different, except that now you have also this term contributes, because here's a tau, so it tells you that p is equal to 0. So there's no momentum flow over the boundary, because the endpoint of the open string is fixed at the boundary, and you take the derivative with respect to tau, so you get a different sign here. Here's a plus sign now. So you get that alpha n is equal to minus alpha n bar. And again, at n, for n integer. And one of the exercises in the tutorials later on will be to derive the boundary conditions if I have mixed boundary to derive the quantization conditions here for mixed boundary conditions. So that you have, for instance, the sigma x vanishing at sigma equals 0, and on the other hand, other side of the open string, that is Dirichlet. Okay, so maybe that's high enough. Huh? Okay. So do you dry clean or wet clean? What have the other people done? Then I do wet clean. Okay, so let's continue. Okay, recall, so what we have found is, so boundary conditions, so they introduce relations between the right and the left movers. Relations between left and right. Okay, so and for Neumann, we have alpha n minus alpha n bar equals 0, and for Dirichlet, just the other sign. And no momentum. How did I call it? P, no? What this means, if you now quantize, this means that, because there's no relation between left and right movers, that an open string has half the degrees of freedom as a closed string. Except that the whole story, the whole quantization progress, you just go through as for the closed string. But you just have one set, infinite set of modes alpha n, because they are related, no? The right movers are related. And you can also show that for both these boundary conditions, so you have your energy momentum tensor, so T of your theory. So this has been, so it's something like the normal order product, dx left, up to some normalization, probably there's a minus sign, minus normal order product, dx right. Yeah. And for both these boundary conditions, these ones, so these are quadratic expressions now in the alpha n's. You insert that here. So because this sign doesn't matter, yeah. So what you find is that for the left-moving Virasoro generators, they are the same as the right-moving, like this, as the right-moving Virasoro generators. In other words, so the boundary conditions preserve the conformal symmetry. Yeah. Okay, so are there questions so far? All very simple. I mean, it's not very deep so far. Yeah. Because Ln, this is the generator of the left-moving and right-moving conformal symmetry. And so one linear combination of these conformal symmetries is preserved. Yeah, this one. Yeah. Okay. Well, this means that there's no momentum. No momentum in the Dirichlet direction. So if you have an open string, say between, and the endpoint is fixed, say on some hypersurface, because the endpoint is fixed, I mean this is the center of mass position, this would be here. Clearly, there's no center of mass momentum in this direction, because they're fixed. This is what this means. But the string can still vibrate. These are the alpha n's. But in such a way that, if a left-moving wave comes in, hits the boundary, it goes back as a right-moving wave. There's a relation between left-moving incoming and right-moving outgoing. This is what the boundary conditions tell you, physically. Okay, yeah, so it's not very deep. Amazingly simple, actually. But has very, very, very many consequences. Okay, so I have to change gears a bit. So there's one subsection now, which might not be, and if you can't follow it, it's not not a big problem, I would say, because I don't know what Neil had really been doing. So if he hasn't introduced partition functions yet, I will do it now, but I will not do it for a closed string. I will directly do it for an open string because I need this concept later on. So one can define a one-loop partition function of the open string. Physically, this is related to what is called the one-loop cosmological constant. It's a one-loop diagram, so there are loop corrections to the background energy of my vacuum, and this is what this one-loop partition function tells you. And it's a certain diagram, a string diagram, so it's a vacuum diagram. So it's just an open string running in a loop. So it's the string analog of a thing like that in field theory. So particle, antiparticle pair created and then destroyed after a certain time. So a vacuum fluctuation. So this is field theory. So field theory. And this is the analog for open string. And so it's an open string here, and it's going once in the loop and then coming back again. Okay? So here's the endpoint of the open string. So this would be sigma equals 0, and this would be sigma equal pi. And this is the time direction, which is, so to say, now compact. Apparently, this has the topology of a cylinder. And here we go. One defines now, so this is just a diagram, but there's a formula for that. So it's called the Annulus Diagram, or cylinder diagram. And it's the integral over what is called the one-loop partition function. Just take it as a definition now. Over what's called the modular parameter T of this torus, which is the quotient of the length, two length I have here, this length by this length. So if I normalize this length to pi, then it's just this length T here. So the length of the cylinder here, of the loop. And C of T, as in thermodynamics, is just a trace over all states in the Hilbert space. So it's a trace over my open string Hilbert space, and this thing is weighted by e to the minus 2 pi t, and then the energy. So in thermodynamics here would be a beta, then it's the Hamiltonian. Hamiltonian is now this thing. So it's the L0 minus C over 24, central charge over 24. Take this as a definition. I define this. So if I have Hilbert space of string excitations, I certainly can define this trace. There's nothing wrong with that. It's just a definition. Just to keep track of how many states I have at each math level, I compute this trace. Yeah? It's the amplitude. It's the amplitude. This I won't explain, but it can be done that this amplitude I've written down here, up to normalizations, of course, is really the one loop string diagram. So you compute so you generalize the field theory formula for all these massive excitations, then you find an expression, which you can, by a certain trick, so you introduce this integral here, which you can rewrite in this form. So in principle, it's a straightforward exercise to do that. But you can find it in textbooks. The question is, so I can define this mathematically, would be nothing wrong with that. In CFT, people just define this. That's to keep track of all states in the Hilbert space. But physically, if you integrate it over this modular parameter, it really gives you the cosmological constant. One loop correction to the cosmological constant from this diagram. Was there another question? Well, the measure is, well, I haven't explained this. This comes from this Schwinger integral you have to do. Schwinger integral. So there's a logarithm appearing here. I managed to remember. There's a formula like by the way, this goes from 0 to infinity. Something like that. Yeah, so if you compute this on a diagram generalized to field theory, there's a logarithm appearing. And then you can rewrite this logarithm by this integral. This is the mathematical. Who was asking the question? This is the mathematical trick you're doing, and this is why this integral comes in. Huh? Okay, but here I think it's sufficient just to, because we are not doing scattering amplitudes or anything here, just take it as a definition. So we can compute such amplitudes, and they are related to this diagram.
This diagram looks topologically equivalent to a closed string just propagated.
Yeah, we're coming to that. You're hitting just the point. I mean, this is the whole point. This is the point. This is why open strings and closed strings are related. This is why ADS-CFT works. Has a chance to work, at least. Okay, so what we're going to do? Yeah, so let's compute this partition function. First, let's just do the oscillator part. So we want to compute this trace. And usually one write it as q to the L0 minus c over 24, where q e to the minus 2 pi t. Yeah, so we have to know the Hilbert space, and I guess Neil has done that for the closed string. So what you do is you define the Fock space, so you define a vacuum, and then you have your algebra. I haven't written this down for these modes, alpha m, alpha n is equal to m delta m plus n0. Yeah, so this algebra helps us to order. So first of all, we define alpha m equal to 0 for m larger equal to 0. So half of the oscillators destroys the vacuum, and the other half creates new state. This is like a Fock space, this is like a infinitely many harmonic oscillators, right? So, and then you can define your states. You start with some negative modes acting on the vacuum, for instance, and then you can iterate that. And this relation here now allows you to order them appropriately. So you have a certain number of I-1 generators. Then you have a certain number of I-2 generators, and so on. And all these possible states, they span your Fock space of your Hilbert space. And the L0 eigenvalue of such a thing, so M1, M2, up to infinity in principle. So the L0 eigenvalue of such a state is equal to the sum of the Mi times, so good notation, times I, sorry. Times I. Now if you count how many, now we have to keep track of how many states we have at each match level, and because here we have the operator L0, so we want to order them with respect to their L0 eigenvalue. Oops. So if you think a bit about it, you find that what you count is just the ways. So if you have a fixed L0 eigenvalue capital N, so what you have to count is in how many ways can I divide N into a sum of smaller numbers such that they add up to N. Now this is the number of degeneracy at each mass level N, and this number is usually called the number of partitions of the number N. And there's a generating function for the number of partitions at each level N, and this is called the eta function. So the generating function, and this is precisely what we are computing here, by the way. So the trace, or the partition function in this case, is nothing else than what is called the eta function, with argument it, where eta of q is the generating, or 1 over eta of q is the generating function of all partitions. So this number here just comes in because of this normalization we have, the 24. And for one free boson C, the central charge is equal to 1. And then we have product 1 minus q to the n, n larger or equal to 1. Which you can expand if you want. So if you write this into the denominator, I just sketch it here, and then you make a geometric series expansion for each term, you see, maybe you should simply write it down, you see that what you, at fixed level, what you get is really the number of partitions of the capital number n. Yeah. Okay. And this is a famous function here. This is called the Dedekind eta function. Which has nice mathematical properties. Maybe I mentioned one. So if you define eta of q, so you find that, or usually it's written like tau, just give you the general definition, and q is equal to e2 pi I tau. This is why I wrote here the I, by the way. So it has a nice property. So if you evaluate this function at this inverse argument, so if you do a duality transformation, you can re-expand it, or you can rewrite it as the old function with the argument tau. There's just the square root of minus I tau in front here. This is a very famous property of this function. And this is sort of, a manifestation, if you want, or the first manifestation. This is like a duality, no? So your theory at small value of tau is related to a theory, in this case the same theory, with a large value of tau. So this is the mathematical analog of a duality, if you want. Which is also a main topic. Not these particular dualities, but strong weak dualities and these things, and T-dualities. It's one of the main issues in string theory too. Okay, but here's just a nice feature, and we are not ready yet. So this is half of the story. There's a term missing. What is missing is because, so this is for Neumann-Neumann, I have mentioned that. This should be for Neumann-Neumann Dirichlet boundary conditions. For Dirichlet, this part would be the same. But for Dirichlet, we don't have any center of mass momentum, but here we have for Neumann-Neumann. So we also have to integrate over the center of mass momentum. So there's a different factor, a second factor, and L0 also contains a factor p squared. So this we have to integrate over as well, because we're taking the trace. So we have to sum over all states, all possible states of the string. So we also have this piece, it comes from the momentum. We have to integrate it over p, center of mass momentum. And this gives us another factor by Gauss formula, 1 over square root of t. So for Neumann-Neumann, we also have here 1 over square root of t. Same square root as appearing here. So this is due to momentum. Yeah, it's obvious, I think. So p. Okay, and for Dirichlet, it's the same without this extra factor for the center of mass momentum. So it's this one. Okay, so now I can define what a D-brane is. I have to erase again. So moving, huh? I think I destroyed this one here. Ah. So, yeah. In this computation, where does the topology of the Riemann surface end up? Well, it's a one-loop diagram in the first place. This is the trace. It's reflected in this trace I've written down. The trace is, so to say, the state running once in a loop and coming back to itself in Hamiltonian formulation. So if you do the same thing for a closed string, you would write down, a torus diagram. Draw a torus diagram. Higher genus surface, much more complicated. It's not a similar formula like that. Simple formula like that. Yeah. Okay. So what is a D-brane? D-brane. So far, I'm just doing the bosonic string. So actually, a D-brane is defined for a superstring. And then it's called a capital D-brane. So this is why I call it a small D-brane, because it's for the bosonic string. So the whole thing lives now in 26 dimensions. So bosonic string has 26 dimensions. Okay, now we have a brane. So now we have an open string. It's all defined indirectly. So we have an open string. Oops. And we have these 26 free bosons. And as I said, now we can require different boundary conditions for these 26 free bosons at its endpoint, say at sigma equals 0. So we are just looking at the sigma equals 0 end. Then we look what kind of boundary conditions can we have, and we can mix them. So we can have, say, D minus 1 Neumann, sorry, D plus 1, sorry, D plus 1 Neumann boundary conditions. In particular also in the time direction. And then we have 25 minus D Dirichlet boundary, Dirichlet conditions. Yeah? So this means that we have D plus 1 longitudinal directions, so where this endpoint can move, is free to move, and transversal to that, it's fixed, so to say, we have 25 minus D Dirichlet boundary conditions. Yeah? And as you say, so the endpoint can have center of mass momentum along the Neumann direction, so this thing can travel here, the endpoint can travel along the brane, but cannot come out of the brane. So this thing, just these boundary conditions for the open string, defines an object in our space-time. So it is an implicit notion. Yeah? We are just studying our two-dimensional conformal field theory, and so to say the coordinates, the fields of this two-dimensional field theory, these are our space-time coordinates, right? So we can have objects, we can implicitly define object in space-time by requiring these boundary conditions for the open string. Good. So then I look at massless. So this is called a D-brane. So this hypersurface in space-time where these open string endpoints are stuck, this defines a D-brane. Okay, this is just, one can do this, but why is it so important? The point is that this object so defined is not just simply a defect somewhere sitting in space-time, that it's dynamical. So this object itself can move, can fluctuate. What this open string theory tells us only is, so to say, it quantizes the possible movements of this D-brane. So in other words, the fluctuation spectrum of this D-brane, this is what we compute with the open string theory. Yeah? There are classical motions as well. The brane can have a momentum itself. It has a position, it has a momentum, it can fluctuate. Yeah, also classically. Yeah? Why is P equal to 0? See it. So why is P equal to 0? This is what I've derived this. So this so dx d tau, this is the definition of a boundary. The D-brane can move, but so you say, so you start with your fixed background. It's always the same story. String theory is a background dependent. We only know string theory in a background dependent formulation. So you fix your background, there's your D-brane. Then I quantize my string. If the D-brane is there, then I see that it's fixed. The endpoint cannot move, it's stuck to the D-brane. Second question is, what are the fluctuations? So now I do quantum fluctuations of this classical background, which is now also the D-brane. And then I find, there are also fluctuations of the D-brane. It can move, it can fluctuate. I will also explain a little bit on that. Yeah. So one has to distinguish these two things. So the open strings, so to say, are just probes. That's a big thing. This is called string theory. We don't know what it is. Yeah. And so we have only probes to find out what this big theory actually is. The best understood probe is the string. You can also probe this theory by D-branes itself and try to define the effective theory on the D-brane. What kind of geometry does that see? This is so to say the state of the art we have for string theory. We only can formulate it. Absolutely, yeah, if you want, yes. Yeah. You mean this one? Well, I mean, there is. I mean, if you know, but just to say, for each end, you have these freedoms. No? But now the brane is different from the open string. So the D-brane is now, now from now on, the D-brane becomes an entity of itself. You know? Before we were just studying strings as probes, probing what the string theory contains. Now we see, okay, there are these different boundary conditions. Now we can ask, so to say, okay, what does these things define? The endpoints surely define such a hypersurface. There's nothing wrong with that. What the string theory now tells us, which I haven't explained yet, is that these things are dynamical objects. And then you can have an open string ending on one D-brane, and starting on one D-brane, for instance, and ending in another. And then there are open strings starting and ending on the same D-brane. The quantization of these strings is always different, depending on what kind of D-branes they feel on the end of the open string. Yeah? Like that? Okay. So if you now indeed consider the fluctuations, so what we have computed here of Neumann-Neumann boundary conditions, and Dirichlet-Dirichlet, so then we have an open string going, for sure, from the brane to itself. Yeah? And now if you look at excitations, the open string spectrum, which is contained in these partition functions I've written down, that's what we do now. So we have at the lowest lying mode, this is alpha minus 1. Now I write an index mu. Yeah? On the vacuum, and now mu is along these directions, and say the indices m are along the Dirichlet directions. So mu runs from 0 to d. Okay, so this carries. So if I now consider this as, so to say, the effective theory on the brane, and this on the brane. So this is my longitudinal space. So this is an index along the brane. And actually, it's a vector index. It looks like a vector in the theory on the brane. So this is a gauge field, which I haven't shown, but has a good chance to be a gauge field. First of all, it's massless. And if you go to light cone gauge, which hopefully has been explained, then you see that has the right degrees of freedom to be the on-shell degrees of freedom of a gauge field in d dimensions, d plus 1 dimensions. So it's massless, and I tell you it's the gauge field. Of course, one has to show a little bit more, has to write down the vertex operator and prove that the scattering amplitudes tell you that this has the right couplings to be identified with the gauge field. But it has already here, you see it has the right properties for this to make sense. And again, at the massless level, so massless level is always one excitation, no? Because the vacuum has -1 energy. There's a tachyon. Also, there's an open string tachyon, by the way, here. Okay, so now I have also the excitations transversal to the brane. These are these guys. They're also massless. What are they? Now I claim, well, they carry an index transversal. So they have something to do with the fluctuation, with the movement of the brane in the transversal directions. So if I think of these as fields, if I do field theory, roughly speaking, yeah, and I give this field a VEF, then I would move the brane in this direction. Yeah? In more fancy words, these are the Goldstone bosons of the broken translational symmetry in these directions. Yeah. So these are Goldstone bosons of broken, because now we have a D-brane there. Our whole theory is not anymore translational invariant, because there's this thing. There's a table, but it's not over there. There's no table, so it's not translational invariant. So there's a Goldstone boson of broken translational symmetry. Sometimes also called a D-brane modulus. So all this is the same. So it's a movement of the brane which doesn't cost any energy. I'll do it slowly enough. So you see, this thing is dynamical. It contains gauge fields. it has moduli. It's like an instanton. So if you have had a lecture on instantons, it's very much the same. In instantons, you're looking for classical solutions of your equations of motions. When you find them, then you find that there are sometimes zero modes of the instanton. Extra things which you can, in which directions you can deform your instanton solutions. No? So these collective coordinates. These things, in some sense, also collective coordinates of this solution. Yeah, for that, then I just have a gauge field in 26 dimensions, yes. There are also space-time, complete space-time filling branes.
So you just made an understand on something,
Yeah.
made an analogy with the instant on something.
It's just an analogy, yes. So if you look from the string, if you look, you can understand the same things. Here I'm doing, so to say, CFT approach, but you can understand them also if you have your 26-dimensional, makes more sense in 10 dimensions, but say if you have your 26-dimensional gravitational theory, so Einstein equation in 26 dimensions, with sources, you have a source which carries some certain tension, then you look for classical solutions of these equations of motions. It's just an approximation to string theory for very small energy excitations. Then you also find, so to say, a D-brane solution, which has these longitudinal directions, and the space perpendicular to that is curved. So these things have been, for 10-dimensional supergravity, they have been described and classified how many solutions do you have. And it precisely matches with the analysis if you do the open string analysis for D-branes. Okay?
Can you have closed D-branes?
Yes, you can have closed string. Okay? You can have D-branes which wrap certain closed cycles in your manifold. Yes, you can have that. So there could be a D-brane, which comes to you and just wraps your entire body. This exists. Okay. That's maybe not a good example, but yeah. Yeah. Where do I have to look? You. Yes? Quantum fluctuation must satisfy the boundary condition. So what the string theory tells you is, so it describes, so you have your classical solution, D-brane. So you can even write down a supergravity solution for that. And now you look for small excited quantum fluctuations around this background. And you want to know what is the energy of these quantum fluctuations, how many are there, and what the open string theory tells you. If you now introduce these boundary conditions for the classical strings, quantize these open strings, then you find precisely the fluctuations of these branes. The open string theory gives you the fluctuation spectrum of the brane. This is what I know. This is what it is. Yeah. Okay, so how much time? 20 more minutes. Okay, good. We have these D-branes. We have these branes, which can have, and for the bosonic string can have any kind of dimension. So there's no constraint on D here. We'll see in the next lecture that for the superstring there is a constraint for D, depending on what kind of superstring theory you are in. Type 2A, type 2B. There are different numbers of, different dimensions of branes in these two theories. This I will hopefully derive. Okay, but here you can see, one could have the idea, just to make a remark, because it's nice, no? There's this gauge field living on this brane. So we know that quantization of the closed string, this gives you gravity. Yeah? So closed string gives gravity. This is something we observe for sure in nature. And the open string quantization, which means D-branes, this gives you gauge fields. Also something we see in the standard model. This is one of the arguments. This is why people are, so to say, excited at all about string theory, because from very simple quantization procedure of closed and open strings, you just get the main forces of nature directly out of that. Okay, the fine print is not yet correct, but at least the rough picture is fine, yeah? So, and you can also have the idea now, because they are living on these sort of hypersurface, they can live on these hypersurfaces. So this is what is called the brane world idea, which I also would like to mention here, that maybe our world is just that we are just stuck on one of these branes, that our four-dimensional world is just four-dimensional, so to say, for the gauge interactions. But if we do fine measurements of gravity, so gravity can always propagate in the bulk, we might find deviations from Newton's law at very small distances. And in fact, people are looking for that experimentally, whether there are deviations. I think the gravitational law, Newton's law, is just tested down to the micrometer scale. So we don't know whether gravity is correct. Its length scale is smaller than gravity, at least Newton's law. Also non-abelian. I will take this is the next point here. Okay, so what we can do now, okay, now if we once realize that branes are things by themselves, and we can just have one D-brane here, another brane here, put them on top of each other, put the branes on top of each other. So what does this mean for the open string? Well, the open string now has selection you can choose between, so the endpoints can be on any of these three sheets. So there's an extra label telling us, hey, my open string, one endpoint ends on sheet 1, sheet 2, sheet 3. So this open string at its endpoints carries an extra label. And people usually write this the following way. They introduce here a matrix, ij, where here's I and j. And this is what's called the Jan pattern label. So it's a fancy name, just for taking care of taking care of on which D-brane one particular open string actually ends. So this gives you a degeneration for the gauge field. But then if you just count, if you have n branes, so n sheets here, n branes, so I and j runs from 1 to n. So I have n square possibilities, n square massless states. Again, now if you compute scattering amplitudes, blah, 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 you find what kind of gauge group could there be? Make a guess. UN, right, UN. So it's SUN cross U1, so it's UN. So from D-branes, at least at this level, we get unitary gauge groups, but we get UN, not directly SUN. And there are at least hundreds of papers written about these U1 factors here. Okay. Yeah?
What I didn't understand is why don't the branes on top of each other don't merge into one brane? So why do
Okay.
they exist
Good question for sure. Yeah. So this can happen, actually this brane merging can happen, but usually, I mean, if something happens dynamically, you gain energy by that, right? So if you have a potential. So precisely what you're saying happens, for instance, if I have branes which intersect, can also intersect, then I can compute the mass of these excited modes, an open string starting here, ending there, and I find, depending on this angle here, I find that sometimes it's tachyonic. Tachyons always indicate decays, right? So tachyons means that there's a certain direction in field space where you can gain energy, of lower energy. Yeah? So for certain angles you find that it can decay. For other angles you find that it's massive, it doesn't decay. And for some of them you find that it's precisely in between, zero, marginal. So in this case both situations are stable. The one where you have both branes or the one where they sort of recombine. You're just on the boundary of these two configurations. And similar here in some sense. So here you're also on this marginal situation. Absolutely, absolutely. You can see what kind of branes are unstable or stable by computing the string excitation. So open strings, if you quantize the open string, this tells you what kind of fluctuations these branes can have. And if there is a fluctuation in which the energy is minimized relative to this configuration you actually started with, then you will see a tachyon. How can you see? Why is it just leaving on the brane? Okay. This is because the moment, I mean, if this state here, okay, this is not the complete vertex operator, so what you have to write down is also e to the pi x. Here this tells you in which directions this state can have momentum. Well, and you see, or you expect, I mean, because the endpoint can only have momentum along the brane and not transversal to the brane. Also, the string excitations only can have momentum along the brane and not transversal to the one. This is why the gauge field cannot leave the brane. It's stuck to the brane. Yeah? This one here, well, I just gave the argument that here you find a degeneracy of massless states. Degeneracy of massless states, because you have this extra label, you have n of them, so you have n square, n times n possible open strings. This gives you a degeneracy of the first excited state. It's a gauge field, so it's just an extra label. I haven't computed, I have to compute scattering amplitude for really arguing that this is a gauge theory. But I just tell you, just from the numbers, you see that it has just the right degrees of freedom to fill out a UN gauge symmetry. Yeah, absolutely, absolutely. To see the UN, you have to have both, the open string has to have both ends of the on this plane. If you have, for instance, a matter field or something, chiral field in the fundamental representation, then the other endpoint just moves to another brane, then you would find a chiral matter field, in this case, in the bifundamental representation of the, say, UN1 living here and the UN2 living here. How do you get the? Good question. This I can get from these guys. They also have a John Patton label in the same way. If they exist, so if there are transversal movements of the brane, these modes transform in the adjoint representation of the gauge theory. Yeah? Another? Yes? Well, it's broken here, of course, no? It's broken, yeah. I mean, even translational symmetry is broken. On the brane, yeah, on the brane is fine, yes. What about haven't thought about this, to be honest. Well, I think this is not, well, the diffeomorphism, so to say, they act on the bulk space-time, right? So you have, think about it, you have your diffeomorphism acting on the bulk, gravity, space-time, and then this, you have extra objects, which, so to say, are also sitting in this space-time. So, I mean, no, I don't think that is the case. This would be strange. I mean, this is, the theory on this brane is a gauge theory, not a gravity theory. What you can talk about is, so to say, something people have discussed, like one loop induced gravity on the brane or something, but I'm sure you're not talking about this in the moment. And also what I have to say, I mean, so far, it's not that, the space by itself is full of branes. You have to, these branes are, they have certain problems. You cannot just have a space, compact space, and put a brane somewhere. I will discuss this later, so there are extra constraints. How much branes you can put on a space, how you can do this, right? So maybe I just continue, or so there are a couple of things I wanted to say. So how many we have here? Okay, I mentioned that. Okay, so this, yeah. Okay, good. Actually, this part is actually ready. So. See. Okay. Well, I actually hope that would come much. We are not very far so yet. I mean, it's not. Okay. So where am I now? Okay. So what already you have realized, and what makes life a bit complicated here is that you have to think of D-branes as indirectly be defined as open string, I mean, the endpoints where open strings can end, and an open string always has two ends, so you're always dealing with two branes. And we'll now see that actually you can give a more inherent definition of a brane. And this is what we are doing now. And this is section 2. And this is called boundary states. So what I will not do in this lecture is to discuss the supergravity solutions. I think that's a point I would like to make clear. But instead, I would like to give you the description in terms of the conformal field theory, which in some sense is more fundamental than the effective field theory description. So, okay, so far we have seen that we have only implicitly defined boundaries, or the D-branes. Let's draw the picture again. So we have two D-branes, then we have open strings in between. And now we'll see that we can maybe give another description of that, of a single brane. What does it actually mean? How can we describe this? Okay, so if we consider this one loop diagram I was already introducing, this Annulus diagram, having its two ends now ending on, say, two D-branes, and then one of your friends here was already noticing that this diagram can either be seen as a one loop diagram for an open string going in a loop, or if you look into the other direction, so if you now consider this as time and this as worldsheet time and worldsheet space direction, it looks more like, well, there's this brane, and it just happens that it emits a closed string, and the closed string propagates to the other side, and there becomes absorbed by the other brane. So the open string one loop diagram is a closed string exchange diagram. Tree level, no loops, just tree level. And this inside, which is actually called loop channel, tree channel equivalence, loop channel, tree channel. So more precise, it's open loop channel, closed tree channel equivalence. Yeah. Why is that? Well, I mean, you still have a two-dimensional conformal field theory which has two worldsheet coordinates. You just have gauged away two of the space-time fields. This is time? I'm not sure whether you're right. I mean, I can also use, I'm working here with Euclidean signatures anyway on the worldsheet. Maybe okay. So let's assume that this can be done. At least this picture, so to say, gives rise to the idea that, so what we can, so a D-brane is an object now which can emit closed strings, has a coupling to the closed string modes. So it's a closed string. We know that the closed string also has excitations, like a graviton and so on. Yeah? What the boundary does, or the D-brane does, it couples to them. So it emits them. I mean, a D-brane emitting a graviton means that the D-brane must have a mass, or a mass density. A D-brane emitting some gauge field, higher dimensional gauge field, means that it has a certain charge. Again, indicating that it's dynamical. And this can be made more precise. So you can describe now this boundary by a boundary state, which is sort of a state in the Hilbert space. It's not completely correct, but it's a sort of a state in the Hilbert space of a closed string. So here we sum over the closed string Hilbert space in this background over all states, and we are, so to say, keeping track of the strength that each state couples to the boundary. Or in other words, the boundary or D-brane is defined by the way how strong it couples to each of the closed string states. So here's a number, alpha ij. This picture gives us the idea that this might be a reasonable definition. So where this alpha sort of encodes, or as a measure, the strength, so say the closed string state ij couples to the brane. Yeah. And this thing is called a boundary state, and is, so to say, the closed string CFT analog or description of a D-brane. I haven't told you what it is. We'll compute this in a moment, but what it is diagrammatically is, so you have with your D-brane, so you now have open, because we have open strings, we have open world sheets, which is a disk at lowest order, and on the disk, which ends on a D-brane, so the boundary ends on a D-brane, and you can have a non-vanishing one-point function of a closed string excitation on the D-brane. So here you insert the vertex operator of a closed string. And the value of all these one-point functions you write in such an object. So these are alpha ij. What ij means, left, right moving. For instance, the state alpha minus 1, alpha bar minus 1 on the vacuum. This I, this j. Or you can have alpha minus 2, alpha minus 1, alpha minus 1, alpha minus 2. You know, this is what I mean. Yeah. But it's important that I'm not talking about closed strings, not open strings anymore. So how can we compute these things? Well, we can do this, but this is very complicated. It can be done, but it's not so easy to compute all these disk diagrams, in particular because there are infinitely many. Yeah? But what you can do is, and it has turned out to be the right way, that what you do is, we know that these D-branes or boundaries, these boundaries, we have certain boundary conditions for the open strings. And these boundary conditions for the open strings can now be translated just by this sigma and tau rotation, so to say, into boundary conditions for the closed strings. Of course, there are no boundary conditions, but what we can require is that on these boundary states, the action of these constraints vanishes. Yeah? And this turns out to be the right way. So what we have to require for Neumann, which was d sigma x before, but now we exchange the meaning of sigma and tau, so now it becomes a tau for the closed string. This is now a closed string. On the boundary state has to vanish. This is what we require. And for Dirichlet, analogous, but now it's sigma. We require that. So what does this mean? So if we now do this for modes, now we introduce the mode expansion for X closed. No boundary conditions directly, but we just require that on this boundary state, this thing vanishes. I think I just tell you what you get. So for Neumann, you find from this condition that now you have exchanged tau and sigma. In fact, it's very similar to the computation we did before, but now the roles are exchanged, so that P of B, the closed center of mass momentum on the boundary state has to vanish, and alpha n plus alpha minus n comes now in on the boundary state, has to vanish. No, the Neumann boundary conditions are for the Neumann directions.
Yes, for the Neumann direction. I mean, you have also a label mu.
Yeah, we have, yeah, okay, now, well, if you want, we can now have a mu here. Okay, fine.
Mu has 1 to 26 or just
Whatever brane you have.
but just for
Mu from 0 to d, and m, which comes in a moment, from d plus 1 to 25. Yeah. And for Neumann, for Dirichlet, you just get the opposite sign here. And that's it. Sorry, no mu m minus n b. So this gives us conditions on these boundary states. So maybe I'll finish in 3 more minutes. Okay, that's okay. Now the organizers, is that okay? 3 more minutes? Ms. Brunner, 3 more minutes?
So you now kind of have a closed string which is glued to the brain.
If you want, yeah?
And then
Yes. The brain emits closed strings. The same way as I'm just emitting gravitons or photons, the brain emits also gravitons. Also photons. Yeah, no, not photons, but gravitons. Okay. So what remains is the solution to these equations. I'll give you the result. The proof is not so straightforward, but can be found in the book or in the lecture notes. Okay. So solution. And remember, when we are able to solve these equations, what we have solved or what we have computed implicitly are all these infinitely many one-point functions. So it's quite remarkable. Yeah? So it's really a shortcut. So I give you the boundary state for Neumann direction. It's very simple. It's just the exponential minus some n equal 1 to infinity, 1 over n, alpha minus n, alpha bar minus n, on the zero momentum vacuum, because there's no momentum, no closed string momentum. And for Dirichlet direction, and if you have mixed, you just combine them, you multiply them. Well, it's just the difference is just this single sign over there, so it just changes this sign to a plus. And here, the momentum is arbitrary. So you have an additional label. So these are the boundary states. So what you now have to do is you have to apply these operators to this exponential term here. Well, then you expand, for instance, the exponential, gives you many, many factors, and then you have to commute through your, not erasing the other, it's called the annihilation operators to the right to destroy the vacuum, and collect all the terms, and then you see that the whole thing vanishes, that you get identical terms which precisely cancel. This is one way to compute. This is very hard and nasty. You better do it term by term. There's a nicer way written in the lecture notes, which is also much more general. It works in many more cases. Yeah, okay, I think this would be a good place to stop. So next time I will continue a little bit with these boundary states, how to compute also the Annulus diagram now with these boundary states, and then we'll move forward to the superstring.